Welcome to the SCI-ED Bandwidth Allocation System demo. For this demo, we have prepared 3 scenarios. Each scenario will be executed on the same topology. The topology consists of 3 ASs that are connected by switch. At the top we have EPFL, which will act as the traffic sink, and at the bottom we have 2 ASs which will act as the traffic sources. On the left side we have CSCS, which will use reservations. On the right side we have ETH, which will not use any reservations. For our first scenario, we will see what happens if a host decides to overuse its reservation. So the host in CSCS will get a reservation of 100 megabits per second, but will attempt to send 300 megabits per second. The first router on the path will notice that the host is overusing its reservation, and it will rate limit it to the 100 megabits per second it has reserved. To the host at EPFL, this is completely transparent and it will only receive 100 megabits per second. Let's now see our system in action. For this, we will take a look at the metrics that are exposed by our infrastructure, as well as the output by the traffic generating applications. On the right-hand side, we can see the input and output rates at our routers. And we can see the input rate at the 2 target hosts. On the left-hand side, we can see the terminal output of our applications. For this scenario, we will only use one host at the top left. We now instruct our client to send the traffic. The sending rate is 300 megabits per second. The reservation it established is only 100 megabits per second. As you can see on the top left, the server only reports 100 megabits per second are received. If you take a look at the top right, there you can see the router metrics at CSCS. The input rate is 300 megabits per second, but the router rate limits the traffic and the output rate is only 100 megabits per second. At the bottom left, you can see the input metrics of the host at EPFL. It only receives 100 megabits per second, as is expected. This shows that rate limiting at the router in CSCS is actually working. Our second scenario will be used as a reference point for the last scenario. In this scenario, each host only sends best effort traffic without any reservations. The hosts in CSCS on the left will each send 300 megabits per second towards the host on the left at EPFL. The host at ETH will send 10 gigabits per second towards the second host in EPFL. The link towards EPFL only supports 10 gigabits per second. The incoming traffic is larger than that and will oversaturate the link, so some packets will be dropped by the router. We now instruct all the hosts at CSCS to send traffic towards EPFL. All the hosts are only using best effort traffic, so there is no reservation involved. As you can see, all hosts are capable of sending 300 megabits per second, and the server also reports that 300 megabits per second are received. So at the top, you can see the router metrics. It gets 900 megabits per second input and it outputs 900 megabits per second. The router at EPFL reports the same numbers. And if you look at the lower left node, the first EPFL node gets also around 900 megabits per second. Now, soon we will start We now instruct the host at ETH to send the traffic towards EPFL. Remember, we send 10 gigabits per second traffic. So now you see how the traffic shows up at the router in ETH. On the lower left side, you can see the receiving rate at EPFL has dropped down by some amount. This shows the impact the 10 gigabits per second going through the same router at EPFL has on the traffic by our CSCS hosts. The server is only capable of receiving around 800 megabits per second now. This is caused by the congestion Now the ETH host has stopped sending traffic towards EPFL. On the hosts in CSCS, you can see how they have recovered and they get full bandwidth again. On the right side, at the router in ETH, you can see the traffic has actually been stopped. And on the lower left side, at the host in EPFL, you can see it receives the full 900 megabits per second again. In our last scenario, we will showcase how our reservation system can protect the CSCS hosts from being affected by the ETH traffic. This time the hosts in CSCS will generate the traffic using a reservation. This means at the link to EPFL, their traffic is prioritized and the traffic generated by ETH will not affect their connection. We now instruct all the hosts on CSCS to send traffic towards EPFL. This time, we still send 300 megabits per second towards EPFL, but we do it with a reservation. So this means we should not be affected by the traffic generated by ETH. As you can see, all the hosts are capable of sending 300 megabits per second, and the server is receiving 300 megabits per second each. If you focus on the receiving rate at the host in EPFL on the lower right side, you still can see the dip that was caused by the high amount of traffic. We now again start sending this high amount of traffic from ETH towards EPFL. Now in the metrics at ETH, you can see that 10 gigabits per second are received. Now the cumulative between the high traffic from ETH and the CSCS is more than 10 gigabits per second. This time there is no dip in the metrics from the receiving host at EPFL. This means our reservations were not affected by the traffic from ETH towards EPFL. Our reservations were respected and properly prioritized. This concludes our demonstration on the bandwidth allocation system.